Howdy. Going to go over, before we get to the example problems, going to go over real quick the conditions that favor SN1, SN2, E1, E2. I have them listed out here in a condensed form, taking basically those 6 sections, I believe, and actually going into 7. I don't know why 7 wasn't included in that. It's a lot anyway, but this is a way to condense it down to hopefully an easier to digest format. Okay? Let's go ahead and use speak. Okay. I have here the conditions that SN2 prefers, that it likes, not that it needs, but this is going to point towards SN2. Conditions here that favor, that point towards, that SN1 prefers. Again, these aren't strict rules. Okay. We don't need to meet every single one either. Okay. And it's just more so like a gradient of things that this one prefers and a gradient of what this reaction prefers. Okay. Also know that just because something is SN1 or SN2 also means that it could be E1 and E2, okay? They don't always have to be one or the other. Notice in our last video we discussed strong nucleophiles and strong bases, and a lot of them are the same. So a lot of these reactions can go through both substitution and elimination. And unless the directions tell you that, you might have to do both in some cases. Usually it'll say, it might like complete the following substitution reaction, and then you just have to decide between SN1 and SN2. Or it could say, provide all the possible mechanisms for this. And be like, okay, I have a strong base and a strong nucleophile. Maybe I could do elimination and substitution. But just a brief overview that, again, these aren't strict rules like that. Okay. Let's start with SN2. SN2 we know is concerted and is going to happen all in one step. Okay. Primary leaving group. Your book says most of the time. In this class, I want to say all the time, but we're going to stick with most of the time. You have a primary leaving group, 99 out of 100 times, it's going to be SN2. Low steric hindrance, everything can happen at once. Okay. You see a primary leaving group, SN2. That's the big one. Okay, we discussed this before. That's the big one with SN2. Okay. Now, when we go through the example problems in the next video, I would maybe have this one pulled up and a different tab next to it. Try the example problems, and you can refer back to this one. That's why we're not going to do it all in the same video here. Okay. All right, SN2. I also have a strong nucleophile. Okay, strong nucleophile, SN2, fast reaction, all happening in one step. Usually I will have a strong nucleophile. Okay. Now with the concentration portion of that, high concentration, and this is, I don't ever remember actually going over concentrations at all with this, but it is included in the book, so we're going to talk about it. If we have high concentration of a strong nucleophile, it's going to favor SN2. So because SN2 happens fast, because think of SN2 as all in one step, it's strong, it's a fast mechanism, okay? So what conditions are really going to favor that? Low steric hindrance, strong nucleophile at high concentration. All those are telling me this is going to be a fast reaction, okay? High concentration of that strong nucleophile. I'm also going to have polar aprotic solvents, okay? Why polar aprotic solvents? Why are those good for SN2? These are not going to interfere with the mechanism at all, where our protic solvents will. Okay? No interference with our solvent. It's not going to get in the way. We're not going to react. Our nucleophile is not going to react with that in any way. It's just hanging out. No interference. It's going to happen fast. It's going to be SN2. So polar aprotic solvent, something that doesn't have hydrogen bonding. Okay? Something that doesn't have hydrogen bonding. I think this is tetrahydrofuran, I believe. Common aprotic solvent, okay? Common aprotic solvent there. All right, poor or good, good or poor leaving groups, okay? So with SN2, if it's a good leaving group, our strong nucleophile can still attack and the leaving group can leave all at once. If it's a poor leaving group, okay, If it's a poor leaving group, it's very unlikely for an SN1 reaction. Notice, because that's our first step. That's our rate determining step. So if we have a poor nucleophile, it's unlikely to be SN1, it's more likely to be SN2. If we have a poor leaving group, we have a strong nucleophile that's forcing that poor leaving group off of that molecule, okay? Whereas in SN1, we just need the leaving group to go on its own. And if it's not a very good leaving group, it's not gonna wanna do that, okay? So there are some conditions for SN2, okay? SN1, pretty much the opposite of all of that. If I have a tertiary leaving group, with SN1, I'm gonna get that carbocation intermediate, and if it's on a tertiary position, that's much more stable. So all of your tertiary leaving groups are going to result in SN1 reactions. 99 out of 100. 99 out of 100 will result in SN1 reaction, okay? All right. Weak nucleophiles. Well, what are weak nucleophiles? Nucleophiles that don't have a formal charge, okay? Remember that before, and then we went halides or strong-ish, weakish, or kind of in the middle. But if we have weak nucleophiles, okay, SN1 as well, removing that leaving group is going to promote a little bit easier access for a weak nucleophile, okay? Low concentration of any kind, low concentration even of a strong nucleophile, okay? This is why these aren't set in stone rules. I could have a strong nucleophile, but if it's at low concentration, it's going to favor SN1, okay? If I have a weak nucleophile of any concentration, it's going to favor SN1. And then also if I have a weak concentration of a strong nucleophile, also be SN1. Only strong nucleophiles at high concentration are really promoting SN2. Concentration is probably the least important here, I want to say, probably. I don't think this is usually a condition that Dr. Andrews or Dr. Morsh have really included in the past, but it's in the textbook. Maybe it's on a reaction arrow. Okay? Tertiary leaving group, sterics, weak nucleophile, low concentrations, polar protic solvents, okay? Polar protic solvents, so now we have a solvent that is going to interfere with our nucleophiles, okay? It's going to weaken our nucleophiles because some of those nucleophiles are going to interact with our polar protic solvent instead of what we actually want it with our starting material, our electrophile, okay? So we're hindering the effect of our nucleophile. We're going to have a slower reaction. It's going to be SN1, okay? Common polar protic solvent, water, methanol, okay? Anything with hydrogen bonding, polar protic solvent, we're kind of messing up our reaction there and making our nucleophile not as strong, not as effective, SN1. Lastly, we need good leaving groups for SN1. We would like to have good leaving groups for SN1. It makes sense because that's our first step, taking that leaving group off, creating that carbocation. Okay, all right. So these are the steps, again, which they don't need to follow, but they promote. So you see these things, kind of use a scale on, okay, there's 3 things that are going to favor SN2, maybe one that favors SN1. Well, which one do I pick? Okay, so it's kind of think of it on a gradient, on a scale there. Again, when we're going over the examples, you can come back to this and look at it for help. All right. E1 and E2, kind of similar here, okay? Again, just because something can do some substitution doesn't mean it can't do elimination, and vice versa. Let's start with E2. Like SN2, we need a strong, before it was nucleophile, strong bases are going to support E2. Everything's happening in one step. We need something strong to be able to do that. Okay? Strong bases, strong bases. A lot of those were our strong nucleophiles as well. Again, that's anything that's stronger than OH. Anything that's stronger than OH in our strong base list we had earlier. Okay? Now, because E2, because elimination is worried about taking only a proton, only a beta hydrogen, which is usually on the very outside of a molecule, okay? usually on the very outside of a molecule. It doesn't really matter if our leaving group, 2 carbons away, is primary, secondary, or tertiary. E2 doesn't really have a preference really on that, okay? So it's not gonna really matter in this case whether we're primary, secondary, or tertiary. We can still do E2 because that proton that it's ripping off is on the very outside of the molecule. There's not much steric interactions going on out there, okay? High concentrations of strong bases. High is similar to SN2, only we're talking about nucleophiles there. High concentration strong bases gonna favor E2. Again, polar aprotic is going to help E2. Polar aprotic is going to help E2, okay? Because our bases are not going to interact with that. They're going to be 100% effective. And we're going to have good and poor leaving groups, okay? Good and poor leaving groups. Very similar to SN2. Very similar to SN2. E1, let's move on to E1 here, okay? Opposite here, weak bases. Weak bases are going to favor E1. Okay. E1's most likely going to happen in tertiary, secondary. Why not primary? Primary carbocations suck. Okay, they're bad. They're bad. Okay. They're bad. All right. I forgot to get something there. I'll do it at the very end of this video. So if you're still watching, you're going to get something that somebody got bored of earlier and stopped the video, did not get. Secondary and tertiary for E1. Okay, mostly just for carbocation reasons there. Low concentration of any kind of strong and weak bases, and even a high concentration of a weak base is going to favor E1. Same rule as before with substitution. Okay. Low concentration of a strong base, low concentration of a weak base, and even high concentration of a weak base is going to favor E1. I don't know how much that's going to come up, but I would include it because it's in the book. Polar protic solvent, it's going to, some of our base is going to interfere with that solvent instead of our reactant, our other reactant, so it's going to interfere with our mechanism, make it slower. It's going to favor E1. And because we have a carbocation intermediate as a rate determining step, we need a good leaving group in order to do that, okay? We're not gonna have a poor leaving group just heterolysis off of our starting material, off of our electrophile. We need a good leaving group for E1, okay? Cool, all right. Now let's take our first video. We learned about strong and weak nucleophiles and bases. Take what we now know about our rules, and we're gonna go over some example problems, and I think you guys are gonna do great.